And today, it's a continuation. So last class we talked a bit about the models as well as the entailment from two perspectives. The first was from a theorem proving perspective, and the second was from a model checking perspective in a very light manner. So we didn't get into depths of that, but I just introduced you to two techniques which is available. So today probably we'll extend a bit and see something called as clausal forms, and these are important to learn because they form the basis of logic programming, or probably the programs which you are going to write. So I'll start with something called as horn clauses. So let us see what is this horn clause. I've given the definition here. It's a disjunction of literals of which at most one is positive. Now, when I tell horn clause, the horn part, it stands for a name actually. I think his name was Alfred Horn, like BNF, backwards norm form. This is another guy who put forward this idea of quickly calculating the truth value of a given formula. So what he told is that if any given formula is of a particular type or a particular format, then you can quickly calculate the truth value of that sentence. So till that time, what happened was probably mathematicians as well as logicians tried to write down the formula in the format which they know and try to calculate the proof or theorems from the written down formula. So this guy comes and tells that, look, if you convert the formula into a particular type, then probably the ease with which you can calculate the whole truth value of a given formula will be easier. So, and that later on came to be be known as horn clauses. And then whenever people develop the logic programming language, they found this to be extremely useful. So that's the story behind horn clause. If you think that why we need to go through these kind of different formats, the main idea is converting into a particular format will help you in finding the truth value quickly. So I talked about constraint satisfaction problems as well as satisfiability problems in the previous couple of classes. Now there also it happens the same. You write a formula in propositional logic or first order logic where the arrow connectives, the biconditional connectives, and a lot of things like that will be there. So you don't need to go through and find the truth value of each and every one. You just convert it into a form in which when you run the algorithm, it finds it easier to solve. One such format is called horn clauses. You might have seen several others, which you will be knowing once I go through these slides. So just check the first item. The definition tells that the horn clause is a disjunction of literals of which at most one is positive. So you can see that each one within the brackets is called a literal. For example, the negative L11, that is called a literal. The V shape, as you know, is the OR, then negative breeze, then OR B11. Each of those components is called a literal, whereas the whole thing is called a clause. Now, according to the horn clause definition, first one is a horn clause, whereas the second one is not, because it tells that at most you can have only one positive literal, whereas in the second one there are two, P12 as well as P21. Now, the beauty of this horn clause is that every horn clause can be written as an implication, whose premise is a conjunction of positive literals and whose conclusion is a single positive literal. So if I convert the first one, not L11 or not breeze or B11. If I want to write it as an implication, I can write it the way which I have shown here. L11 and breeze. If L11 and breeze, then B11. Why is it so? Why did I write the first one in an implication form? Is there any reason for that? Or why did I write like that? Look, every implication P implies Q can be equivalently written as not P or Q, isn't it? P implies Q is equivalent to not P or Q. So here in this part which I have shown, if you take the first part as P, implication as implication, and B11 as Q, then when you put the negation, it actually happens outside the bracket. When the negation happens outside the bracket, and when you try to prove negation first applies on L11, it becomes not L11. Negation applies on conjunction, it becomes or, and negation applies on breeze, it becomes not breeze. Implication becomes or, and then B11 remains. So that is the idea. So any implication can be written equivalently as a clausal form. And why do you need that? Because in any English language you try to convert, you will be having a lot of implications as well as biconditionals. The idea is to remove them one by one and bring it into a clausal form where only or clauses or and clauses happens. So horn clauses like the above one, the first one, with exactly one positive literal are called definite clauses. And definite clauses form the basis of logic programming or the prologue programming it is called, which you will be seeing in your lab classes. Why I didn't start lab is because I have to clarify with the dean whether we are continuing with the lab classes this time or is it pushed to the next semester. Once I get the clarification, we'll start. So the logic programming language which you will be seeing for your practicals is called Prolog, and that is and Prolog uses a lot of definite clauses or only definite clauses, and that is why we are learning something called as horn clauses. Now inference with horn clauses can be done through forward chaining and backward chaining. So there are two techniques which is available. One is called forward chaining and one is called backward chaining. I hope you have, you might have come across that forward chaining as well as backward chaining. How many of you heard about forward chaining and backward chaining? Anybody?
Yes.
Okay. So beauty is that deciding entailment or whatever we saw in the previous class with horn clauses can be done in time linear. That's what I have written. It hasn't come up. I think probably I blew up the font. So it can be decided in time linear. That is the idea. So definitely you have to learn about horn clauses. Now I've given an example here for those who do not know what is forward chaining. KB stands for knowledge base. Now instead of writing all rules and facts in the knowledge base which we have seen in the previous classes, in today's class what we will be doing is we will be probably putting it as a conjunction of horn clauses. So that becomes easy to do the proofs. So KB is equal to conjunction of horn clauses. It can be used with forward and backward chaining. And these algorithms are very natural and run in linear time. So the idea of forward chaining is what I have written in that item. Fire any rule whose premises are satisfied in the knowledge base add its conclusion to the KB until query is found. So obviously you have to have a query to start with. Query means what is that you want to prove. Now, if you have that and you are given a conjunction of horn clauses, how to do forward and backward chaining is the question. So 7 things or 7 statements I have given in that knowledge base. Now, if I have to use forward chaining, where will I start with? I'll give you a clue also. Suppose I want to find Q. Q is my query. Then how should I start this forward chaining process for this particular knowledge base? Q is that I want to find. I have been given a set of clauses. I mean, some are in rule format. Obviously, you have to convert that when you do the programming. But this is a very simple question I have given here. And I have also written down forward chaining what you should do. So if any one of you can tell me what could be the first step. My query is Q. Which one will I fire?
Sixth rule.
Okay, correct. So if any rule whose premises are satisfied in the knowledge base, now there are only 2 things which are actually satisfied from a very, what you call atom or atomic point of view, which says that the 6th statement A is true in that knowledge base, 7 statements B is true in the knowledge base. So you have to fire one by one. So you fire A, then you fire B, together you get A and B. From that, you can fire the 5th rule, A and B implies L. Then from that, so you get A, B, and L. From that, you can fire the 3rd rule, B and L gives M. So you have A, B, L, M. Now B and L gives M, L and M gives P. So you get till P, and from P you can get Q. So this is the idea of forward chaining. Very simple idea. Similarly, you can do the backward chaining procedure also. So for backward chaining, work backwards from the query queue, whereas in the forward chaining, you work forward from the existing atoms and reach the query. To prove query by backward chaining, check if Q is already known, or prove by backward chaining all premises of some rule concluding Q. Avoid loops check, loop check if new subgoal is already on the goal stack. Avoid repeated work and check if new subgoal has already been proved true or has already failed. I mean, this is a very simple explanation of forward chaining and backward chaining. So the idea is that if you convert it into horn clause, then the way you can do forward chaining and backward chaining becomes easier rather than having a rule set kind of thing happening in the knowledge base. So that's the main idea of these 2 slides. Now there is a question which I have given here. You have to, so I told you when the start of the class, these people, and we started with horn clauses, and I told why every propositional logic formula should be converted into a clausal form. That is for ease of computation. Similarly, you guys might already be knowing about CNF and DNF. So CNF means conjunctive normal form and DNF means disjunctive normal form. Now suppose I ask you what is conjunctive normal form, what will be the answer? A very simple, quick answer, conjunctive normal form. Anyone? You have heard about conjunctive normal forms, right? Hello.
The clause will be conjuncted with, it is a conjunction of one or two clauses.
So it is a conjunction of disjunctions,
One of,
basically. So inside the brackets, you will be having disjunctions, and outside the bracket, main connective will be conjunctions. Okay. Now, can you tell me why this is being done? Look, usually if it is an offline class, I ask a lot of questions, so that is why I keep asking. Is there a reason for doing this? Why have you ever thought about it? Why is that you need a conjunctive normal form or a disjunctive normal form? There should be some reason why they are doing all this. No, it is not that they don't have any jobs or these mathematicians or logicians sit and convert all these formulas into a specific format. Anyone can answer if you are there.
Sir, it becomes a bit more deterministic.
Sorry?
It becomes a bit more deterministic.
By generous, what do you mean? Why should it become more generous?
Like for one input, there will be only, for one rule, there will be only one output or result.
No, you are all computer science, going to be computer science graduates. So probably from a computing perspective, you can try to answer. These all remains propositional logic formulas. That is okay.
like it's easy to implement in computer circuits like AND gates and OR gates instead of implies and double implies.
But why is it easy to implement? Because it is only OR gates and AND gates. Okay, so suppose you are given a formula like the one I am showing in the slide. B11 if and only if P12 or P21. Now, when you convert this into a particular conjunctive normal form, as far as satisfiability is concerned, because you want to check whether, if even if it is an OR gate and gate in a circuit also, you would like to quickly find whether one path of the circuit is satisfiable or not. Now, if I give it in the format which I have shown in the slide, it becomes very difficult. Why? Because you have to work down all the truth values. I mean, the entire truth table you might have to check. If you give it in a clausal form, especially in conjunctive normal form, the moment you find one of the clauses is false, you can immediately cut off that branch. Why? Because it is a conjunction of disjunction. And in a conjunction, the moment one part is false, everything else goes to be false. So that is the advantage of converting it into a clausal form. If you think like a tree-like structure also, the moment you have conjunctions of disjunctions in a branch, and it turns out to be that the first node is false, immediately you chop that off and backtrack, go to the next branch, and you continue. In the disjunctive normal form, it is a disjunction of conjunctions. So the moment you see something within a bracket, one of them is false, that at least that one bracket can be shifted out. You don't have to check for the remaining one, because you all the time you know that that is going to be false only. So basically it is ease of computation. It is ease of basically the search process. Whatever search you are doing, whether it is a breadth first search, whether it is a depth first, whether taboo or whatever you call. So these kind of things, lot of things happen in the constraint satisfaction area as well as circuitry. It becomes easy for you to calculate the truth value of the whole formula by calculating quickly the truth value of the nodes or the branches. That is the main idea. If you if you think that probably why these people are doing this, So here I have given a question. Usually I ask people to do it, but we will see how in the final leg, what is the CNF, or how does the CNF appear? So one question of this type you can expect as far as the first minor is concerned. Because usually I told you it will be like a problem solving thing. So first question related to problem solving is coming into conversion to CNF. So you can note down that. I'll tell you all the questions beforehand. I mean, not the actual questions, but the kind of questions which could come. So you can note down. One is conversion to CNF. So I have written down everything here. So eliminate the biconditional, replacing biconditional with implication. A kind of formula we saw in the last class also. So when you eliminate the biconditional, obviously you get a formula like this. B11 implies P12 or P21 and the other way. P12 or P21 then B11. That is the first step. Now, if you can tell me what could be the second step, anybody? So the first step is to eliminate the biconditional, replacing it with the implication, which I have done. Now, what could be the second step?
Removing the implication.
Okay. So eliminate the implication, replacing, that is something else has come, I have to remove that. So now I remove the implication. So the first part, not B11 or within brackets, whatever was there, I have pulled it out. And same case with the other part. The negation is happening outside because P12 or P21 is together and the implication becomes OR. So like that, you keep doing. You move the negation inwards using all those rules which you already know, and double negation. Can somebody tell me the next step? Any idea? Because you need to have a conjunctive normal form in the end. That is a conjunction of disjunctions. This is not the, yeah, this is a conjunction of disjunctions, but with three clauses. But here in the second one, something is happening.
Distribute the disjunction over the conjunction, which we get from De Morgan's law.
Okay. So this is what somebody was answering now. So you have flattened that. And now you can see that this is, it is not a 3-sat problem, yeah, because one is 3 and one is 2. Okay. So if you go and check the literature, you can find that, I mean, for a large number of variables, if you convert it back into a satisfiability problem, if you have 3 clauses, if you have 3 clauses in one, it is probably difficult to solve rather than having a 2-clausal formula. So these are called as 3-sat problems and 2-sat problem. I don't remember exactly now, but one of them, I think it is the 3-sat problem, is an NP complete problem. I have to check that. So now for this class, you don't need that. So here the idea is to convert it into a conjunctive normal form. Given any formula, I mean, look, I am actually playing only with very less number of variables here. That is to make you for ease of understanding. When I tell about SAT problems or constraint satisfaction problems, I told you you have to think about large number of variables, 40,000, things like that. So then probably coming up with a circuit or coming, it turns out to be really difficult. You have to have different ways of solving such a big graph. Even if you take the graph coloring problem also, I mean, probably it may not be, the toy problems may not be having that many number of variables. But the actual problem domain of these kind of applications are, I mean, the tune of where the number of variables goes is very huge. Even the competition is that. So you have to develop algorithms where you can solve at least to the tune of 40 to 50,000 variables. And everything should be in something like a conjunctive normal form, a clausal form. So that was the first thing of this class. What is Horn clauses and how to convert any given formula into a CNN. Now there is another important technique, which a very simple technique, but probably nobody thought about it. And then this guy called Robinson came one fine day and told, look, if you want to solve certain kind of Horn clause problems, then you can apply something called as resolution. I think he won some awards for that. So we will see two types. One is the normal resolution and one is the refutation one. I have given two examples here. First is phi 1 is equal to A or not B, and phi 2 is equal to not A or B. And then I am telling that the resolvent of phi 1 and phi 2 is A or not A, B or not B. Now, why it has come up like that is because how resolution happens is it deletes the one pair of complementary literals at a time. Complementary literals means one positive, one negative. So if I take phi 1 and phi 2, in the first attempt, not B and B gets cancelled, so you get A or not A. In the second, A or not A gets cancelled, you get B or not B. Now I have written here, note that only one pair of complementary literals may be deleted. I mean, that is for understanding purpose. Even when you implement, it is like that because you have to get the number of clauses should be counted. So that is the idea. So one pair of complementary literals you delete each time. Whatever is remaining becomes the resolvent. That is how I have got the resolvent of phi 1 and phi 2 in this brackets. First not B, B gets cancelled, A or not A you get. Then A not A gets cancelled, you get B or not B. Now I have given two questions. You should be, because this is very simple explanation. So you should be able to tell me what is the resolvent of phi 1 and phi 2 for the first item. Phi 1 is A or not B, phi 2 is A or not C. Anybody? A or not B, A or not C. I told one pair of complementary literals may be deleted at a time. What is the resolvent of phi 1, phi 2? You guys are there, right? Anyone? Did you understand what I told in the slide, the first one? What is resolution? Nobody is answering. I think nobody is.
Yes.
Yes, sir.
Okay. So did you understand the concept of resolution?
Yes.
So what is the answer then for the first item?
So is it A comma not B or not C?
No.
We don't have any complement pair here.
So that answer is correct. So you cannot find a resolvent for that. The definition I have given that only one pair of complementary literals may be deleted. There are no complementary pair of literals because both A's are positive, one is not B, one is not B. So resolvent is an empty set. Okay. So next one you can find, that is okay, A or not B or C, not A or not B. So first A and not A gets cancelled. You get B or not B or C, and that will be the answer. There will not be any more resolvent. So whatever definition I give, you stick to that. You may not be able to find an answer. That is okay, you write. There is no pair of complementary literals, so it cannot be solved. Now I have given a set of five clauses, no implication or anything. The task is to show that the set 1, 2, 3, 4, through resolution, you can prove 5. That is what it means. This, which I have highlighted, it means from 1, 2, 3, 4, through the technique of resolution, you can prove 5. And 5 here is C. 5 is provable from 1, 2, 3, 4 using resolution. The idea is to show how that is possible. So rather than troubling you, I'll give you the answer. This was what I had written it down here. Yeah, A or B or not D, A or B or C or D. One more answer. Okay, yeah. So I have given 1, 2, 3, 4, but in between I did a resolution. So whatever I have written hypothesis, that is the one which is given to you in the question in the previous slide, this slide. And whatever resolving I am doing, I am actually showing. So first two you take, you obviously know that not D, D gets cancelled. You get A or B or C. And not B or C is already given. With that, again resolving, you get A or C. Then not A is also given in your question. So you get phi is equal to C. That is what I had asked in the previous one. Task is to show that you have to prove C from 1, 2, 3, 4. So these are very simple things. So from simple, I would like to come to complex towards the end of the lecture. I hope you have understood this. I mean, if you just observe, that is enough to understand these slides. So resolution, and this is the normal resolution proof. I mean normal in the sense, this is the direct resolution proof. There is one more. Okay, this is the diagrammatic representation of the resolution proof which we did by hand. This is for ease of understanding I have put. But if you have already understood from the previous slide, then you can probably ignore this one. Now there is, so first one is the normal resolution or the straightforward resolution. There is also one more which is called resolution refutation. You might be already knowing this from some other subject point of view, especially mathematics, which is called proof by contradiction, or here it is called resolution refutation. So resolution is refutation. I have tried to put it in one slide. Actually, this is a very important concept which is slightly difficult to understand. And since it is online, I hope you will understand this slide. Otherwise, you can write to me and probably check it out. First, I will read what I have written it down, and then I will try to explain. For direct inference, resolution is not complete, even when the goal is a simple clause. So completeness, you know, I have already sounded off in the previous lectures, completeness and soundness. One example I have given here for why I am telling that for direct inference, resolution is not complete. Very simple example I have taken here. Suppose phi1 is equal to A and phi is equal to A or B. One is a standalone literal, another one is a disjunctive literal. Then it is clear that from phi1 is what? A. Phi follows. That means if you write something A, you can obviously add a disjunction to that. There is nothing to worry about it. Nothing is wrong because either A or something else you are telling, and it is always true unless and until you have the first one true and the second one false. So you can always add something to the right hand side of a disjunction. This is what it means. Yet phi is not an element of res phi1 phi2. What does it mean? You have phi1 as A, you have phi as A or B, and in the normal settings you can tell that A or B follows from A alone. But if I want to prove it through resolution, I cannot. How can I prove it through resolution? How can I prove A or B from A through resolution? It is not possible because resolution tells that it needs two complementary literals, right? So you cannot prove. This is what the first step. However, resolution is complete for refutation. That is, proves for falsity. Let us see. To solve the above example, negate the goal and add it to the hypothesis. So when you negate the goal, what was the goal? The goal was A or B. You had to prove A or B from A. So A or B is the goal. What it says is, to solve the above example, negate the goal and add it to the hypothesis. So the negated goal becomes not A or B, which is not a clause, but a simple application of De Morgan's will give you not A and not B. Not A and not B is not a clause, but it may be decomposed into two clauses, not A and not B. So now what do you have in your knowledge base? A, not B. The problem of establishing that A or B follows from A is thus reduced to the problem of establishing that, why it is going down, I don't know. Yeah, establishing that A, not B will result in falsity. That is the most important part you have to understand. In the first case, I told direct inference resolution is not complete, and I showed why. Because you cannot resolve phi1 and phi2 and get the answer. Because phi1 is A, phi1 is A, and then from phi1 phi follows, yet resolving phi1 and phi will not result in what you call the answer, the goal which you want to get. There is some mistake here because phi1 gives phi, then again I have written phi1 and phi2. But anyway, I hope you have understood the logic. But if you actually take the refutation procedure, then you can negate this. What you want to prove, you can negate, and then you can find a contradiction and then tell that therefore A or B follows from A, because negation of A or B does not follow, which means A or B actually follows. This is the idea. So through resolution refutation, you can find that A or B follows from A, but through direct inference, you cannot tell that A or B follows from A. This is the idea. Once more, I'll tell you. From A, you can get A or B. There is no problem. But if you apply the resolution procedure, you cannot prove that from A or B follows. First thing. Second thing, you want to prove A or B follows from A. Okay. What you usually do in proof by contradiction is you take the negation of the conclusion and tell that the original one you started with ends up in a contradiction. Therefore, the negation is false, whereas the non-negation will be true. This was the idea, proof by contradiction. Here also, we are taking the same thing. You are telling it is not the case that A or B follows from A, and then you are coming up with a contradiction, which actually means A or B follows from A. So, for proof of contradiction, or here, resolution by refutation is complete, whereas direct inference resolution is not complete. I will stop here and ask how many of you understood what I told, how many of you did not understand. You can tell frankly, no problem. If you did not understand, please tell. Otherwise, I won't know. Have you understood? No answer.
Yes.
Yeah, wonderful. Okay, good. First time. Okay. Now, the same principle I am applying for the previous example. In the previous example, we directly did the resolution and we found C. Now we have seen resolution by refutation. So we'll see what this is. Now the task is to find from 1, 2, 3, 4, and when you add negation of C through resolution refutation, you get falsity. This is the idea. Again, pretty much same. Hypotheses are the premises which are given to you, A or B or not D, A or B or C or D. From that, resolving on 1 and 2, you get this. Only difference comes here is, what will be the only difference in this question?
Negation of
Negation of?
the fifth hypothesis. When we do that,
Yeah, negation of C. So 5 is, you actually add as an hypothesis this one, 8th step,
yes, sir.
and then you get a contradiction. So when you get the question, it will not be pretty straightforward like this. You have to check whether I am asking for resolution by refutation or the direct resolution, and accordingly you answer. So 3 things we did today. First was conversion of any given formula into CNF, and similarly DNF also you can do. I didn't show that because there is no need. Any given formula, you can convert it into a conjunctive normal form or a disjunctive normal form. The second one we saw was Horn clauses. And when you have a set of Horn clauses, how do you do forward chaining, backward chaining? Third one is resolution proof, direct resolution proof, as well as resolution refutation, or in a way you can tell that this is proof by contradiction, and the diagrammatic proof of what you have seen in the previous slide. Now this is, those were okay, very simple things for your understanding. The kind of questions you are going to get for the exam is of this type. You have to clearly understand this. It is resolution. You might think it is easy till the last slide, but it is not. I am moving back to the Wumpus world example. We saw a model-based proof. We also saw theorem proving based proof, as well as model checking based proof. But now you are going to see a resolution based proof for the same example. Again, just to refresh your memory, when the agent is in 1, 1, there is no breeze. So there can be no pits in neighboring squares. Therefore, the relevant knowledge base is R2 and R4, because this R2 and R4 I gave earlier. If you remember, I don't know whether you have noted it down. R1, R2, R3, R4, R5 I had written. So I am pulling out only two important things which I need to solve this problem, that is R2 and R4, and I have given it here. R2 is B11 if and only if P12 or P21, and not B11 is R4. And what is that you have to prove? You have to prove alpha, which means that you have to prove there is no pit in 1, 2. You have to demonstrate the resolution proof for this. Any one of you can think about, first you can think about whether there is any complexity involved in this to do this. If there is, you can tell me what it is, and then you can show me or tell me how could you do the resolution proof. So R2 and R4, if you are doubting what it means, I'm just going back. Oh, okay. It's in the previous lecture 4. You remember now how we wrote that R1, R2, R3 and R4? Is there any complication in doing this? That is first question I want to ask. If at all it is there, what could it be? How will you solve this? Through resolution.
Should we like convert that KB into a CNF like with all?
Exactly. Correct.
Yes.
First one is that. So I think we did it in the previous slide. B11 if and only if P12 or P21. I think that is the same thing I have asked here. Correct. So you first convert that into this format. Okay. And
Yes.
whatever I have given here as 4.1 is what you get as the clausal form. So this has three things, three conjunctions, three clauses, sorry, not conjunction. It is a conjunction of disjunction, so three clauses you have. Along with these clauses, what will you put?
Negation of alpha.
No, three clauses. You first tell me how many clauses will be there. Let me see whether you are getting right there.
The 3 in the previous one and there's one more here.
One more here, that is not B11. Okay, good. So 4.
Yes, sir. 4 are there.
So one answer is 4. Any other answer? This you have to do resolution by refutation. Okay. This example is for that. So somebody told it is 4. I'll show you the next slide. You will not be able to see clear, so I'll just blow it up. From seeing the answer, you tell me what is that I have done. I'll just blow it up. Too much I blow. Anybody can tell me the answer. This was the question. And for ease of understanding, so somebody told 3 from the first, then this 4. You can see this, no? Is it clear? Okay, I'll blow it up. So he told the 3, that is 1, 2, 3, first 3. Then he told that negation of B11. What is this B12?
The negation of
Negation
alpha.
also.
Very good.
Negation of
So
the
the negation of the conclusion. Now tell me what these arrows mean and how the resolution proof goes. And this is the kind of questions you can expect for your exams. Previous ones, for just ease of understanding, I told you I'm repeating again. How did I get those bottom boxes? There might be some mistakes in the bottom boxes, but that is in late tech I did one or two might have gone here and there. So that is okay.
So those are one of the possible resolutions.
No, that is okay. But you tell me at least one how it came out.
Not P2, 2-1 or B11, and the second box, the in the upper row,
So in the
B,
upper row, which boxes you are taking?
the left two,
Left two, he is taking. Good, very good.
and we remove the P21 and negation of P21 complement pair.
Okay. So first he is taking the first box and the second box. He is trying to find there is whether there is a negative literal in the first box and a positive literal in the second box. Yes, there is. Not P21 and P21 is there. He cancels that, and then what remains in the first box is B11, and in the second box it is not B11 or P12. He is pulling that out and putting it in the first box at the bottom. Correct.
yes, yes.
But is there only two complementary literals happening or more?
More there are
More, sir.
Yeah,
B11 and not B11.
exactly. So that gives the second box. Now, what about the, so the arrow is also changing. One is dark arrow, one is line arrow, one is dotted arrow. So what is happening there? So if you see the dark arrow, first box and second box, you got the first two boxes down. Then I went to the third box and first box and third box. Is there anything to cancel? Not P21, not P12 or B11. It will
no.
not cancel, isn't it?
Yes, sir.
Then I went to the fourth box, not P21 or B11 and not B11. So there, not B11 will cancel with B11 and the remaining I am getting not P21. That is why there are three dark arrows from the first box. And the first box and the fifth one, there is nothing, no cancellation. So whatever complementary literals I am getting, when I combine first box with second box, first box with third box, first box with fourth, and first box with fifth, I am using a type of dark lines to indicate that. Similarly, second box with the other boxes, third box with the other boxes, fourth box with the other boxes, etc. etc. And finally, when you work it out, you will find that there is a contradiction happening between the negation of the conclusion which you took as well as one of those bottom boxes. So you are coming up with a contradiction which tells that if you take the negation of the conclusion, you are arriving at a contradiction. So the original one follows. So pit in 1, 2, you are not able to prove, but there is no pit in 1, 2, you are able to prove. You have to work through this. I can only state one example in which it follows. I am telling you again, there might be a slight mistake in one of these boxes. Maybe you can take it as homework and point it out to me in the next class. I think 1, 2 or 2, 1 somewhere because and I was checking night, but I couldn't fix that. So this is what is called, so when you write an algorithm to solve any propositional formula by way of resolution refutation, this is how it should work. Now, do you have to go through all this process to find a contradiction? Need not. You might arrive at a contradiction before itself. So you can stop and you can tell that, look, halfway through I arrived at the contradiction, which means the negation of the conclusion does not follow, but the original conclusion follows. This is the idea. Okay.
Yes.
So that is the resolution proof. Again, I think I'm falling short. I think I have taken it only till here. Maybe from I have the other slide. You are able to follow, right?
Yes, sir.
Yes, sir.
So then